Hi, my name is Sung Jae-moon from Sungkyunkwan University. In this talk, I will introduce our paper titled Boosting WorldTP Performance with Per-Page Logging on MVDIM. By storing per-page little logs in MVDIM, we can dramatically reduce writes to SSDs. This also enables little-list under-list recovery and redo-based multi-versioning. This work was done at the Technical University of Munich, Korea University, and Seoul National University. Let's talk about the background and motivation. The OLTP workload frequently issues small random updates, which lead to excessive writes to SSDs. Since write operations are slower than read operations on SSDs, fast reads stall behind slow writes. Therefore, in SSD-based database, writes are a major performance bottleneck when running OLTP workloads. So, how can we reduce write traffic to SSDs to improve the performance? The idea is simple: storing only updates in a fast and durable cache. Then, what kind of cache is best for storing smaller random updates? We can consider NVDMN and DiskPMM as fast and durable caches. Compared to DiskPMM, NVDMN offers a lower write latency, finer access granularity, and less read-write asymmetry. Therefore, we decided that NVDMN is the best cache for OLTP workload. However, NVDMN has small capacity and is costly per gigabyte, so we need to think about how to use this limited and expensive NVDIM space efficiently. To measure how much data is actually updated before a page is written to storage, we track the size of little logs per page write. We found that most OLTP pages are written to storage due to small updates, typically under 256 bytes in a 4 kilobyte page. This implies two things. First, the database suffers from 16 times durability overhead in DRAM SSD two-tier architecture. Second, writing only little logs is enough to ensure durability, not the entire page. Then there are three approaches to ensure durability. First, writing a page to SSD. Second, caching a page in MVDIM called MVSQL. Third, caching per-page little logs in MVDIM called MVPPL. We estimate the durability cost of each approach using the 5-minute rule. Based on the analysis, we adopt caching little logs in MVDIM. Since it can ensure durability faster and cheaper than other approaches. Moreover, it can use MVDIM space more efficiently compared to page caching approach. In this section, I will explain the basic framework of MVPPL. To support MVPPL, we add two extra data structures, DRAMlog space and a lookup table. The normal page refers to a regular database page. When a normal page is updated, we write the per-page little log for this update to the DRAMlog space. We refer to this per-page log as a PPL. In addition, we also write the separate little log to the little log buffer. After an update, when a page is returned to storage due to checkpoint or replacement write, we allocated the MVDIM space to the page. The allocation unit size is 64 bytes, which is the granularity of the MVDIM. We copy PPL to each allocated space. We add this entry to the lookup table for later access. And then, we skip the page write since the updates are already durable in MVDIM. From now on, we refer to a page with PPLs in MVDIM as a PPL page. Then let's talk about how we can skip the page write for a PPL page. When a PPL page is updated, we directly append the PPL to the NVDIM space. After update, when a PPL page is returned to storage, we skip the page write for PPL page since all updates are persistent in NVDIM. With this framework, MBPPL can reduce page writes to SSD by caching per page little logs in NVDIM. However, there are some issues. Firstly, how can it efficiently use the expansive NVDIM space? The solution is selectively allocating NVDIM space based on the total size of PPLs for each page. It means that if the total size of each PPL is less than 256 bytes, MBPPLs skip the disk write for the page by storing PPLs in NVDIM. Otherwise, we just write the page to storage. This threshold is derived from the per page update size, as discussed in the background and motivation section. Let me explain how it works. If a normal page is written to storage, we decided to write this page to storage, since total size of its PPLs exceeds 256 bytes. In the case of a PPL page, when a PPL page is updated, since total size of its PPLs reaches 256 bytes, we stop allocating additional NVDIM space to the page. From this point, we mark this PPL page as dePPLized. It means that this PPL page is not drawable by the PPLs in NVDIM. After update, when the dePPLized page is returned to storage, we write this page to storage and reclaim NVDIM space for this page. By selectively allocating NVDIM space to the page, we can avoid wasting NVDIM space. Another issue is increased read latency when reading a PPL page from storage. It's because we need to read the old page from storage and apply PPLs to reconstruct the up-to-date page. However, since the total size of PPLs is limited, the read latency is increased slightly. Nonetheless, the benefit from write reduction far outweighs these overheads. The last issue is that, since NVDIM space is limited, it can eventually run out. To prevent this situation, we reclaim the NVDIM space among the current PPL pages. We use two types of NVDIM space reclamation. First, foreground reclamation targets PPL pages in the buffer that use a lot of NVDIM space. Second, the background PPL cleaner targets unused PPL pages that are not in the buffer. By routing these PPL pages to storage, we can reclaim NVDIM space and prevent it from running out. Also, we place the double life buffer and little log buffer in NVDIM to reduce logging overhead and to remove redundant writes to SSD. Let's talk about the recovery. Based on Ares recovery algorithm, we made minimal change to the recovery process of vanilla MySQL. During the analysis phase, MBPPL scans the NVDIM to reconstruct the lookup table. With lookup table, we can distinguish three types of pages: normal page, PPL page, and dePPLized page. For a normal page, recovery is the same as in vanilla MySQL. apply little loss to the page, and roll back updates from uncommitted transactions. For a PPL page, we scale little phase and under phase, since all updates are durable in NVDIM. When we read the page after recovery, we apply only the PPLs generated by committed transactions. Lastly, for a DPPLized page, it can be updated after DPPLized. Therefore, we apply these PPLs to the page. After that, recover like a normal page. With this algorithm, we can recover all types of pages. Databases keep multiple versions to support concurrent data access. However, undo-based versioning is known to have poor performance in HTAG. It's because constructing a visibility pool requires reading multiple undo pages from storage. To eliminate the overhead of undo-based approach, we support redo-based multi-versioning by leveraging PPLs in NVDIM. PPLs are stored in chronological order per page, so we simply apply them up to the required timestamp. This approach needs only a single page read, while undo-based needs to read multiple undo pages. This was the evaluation setup. We configured all systems to have equal total memory cost. So, if MBPPL uses 1 GB of NVDIM, we reduce DRAM by 3 GB in MBPPL. It's because NVDIM is 3 times expensive than DRAM. In terms of write reduction, MBPPL reduces per transaction write traffic by 81% and 62% compared to vanilla and MB-SQL. By reducing page writes to SSD, the SSD can handle more reads, therefore MBPPL can achieve higher transaction throughput. It means that MBPPL transforms the I/O pattern from write-heavy to read-heavy. So MBPPL can leverage the fast read performance of SSDs and extend SSD lifespan. However, MBPPL has some overheads such as a lower hit ratio and extra CPU uses. The lower hit ratio comes from reducing DRAM to match the total cost with added NVDIM, and the extra CPU usage is due to writing PPLs and applying PPLs to the page. These overheads are not negligible, but they can be justified by the higher transaction throughput. To analyze effect of evidence-based reclamation, we run TPC's benchmark on 3 versions with 6 million transactions. Without space reclamation, MBPPL's performance degrees due to running out of evidence space. With space reclamation, MBPPL maintains the throughput consistently. Although it introduces some read and write overhead, this overhead underscores the benefits of evidence space reclamation. Next, we run the TPCC benchmark while varying the NVDIM to DRAM ratio. MBPPL consistently outperforms adult systems at all buffer sizes. Moreover, MBPPL can achieve higher transaction throughput than vanilla with just 1/5 the memory cost. We also found that MBPPL consistently outperforms vanilla across all SSDs. Interestingly, the performance gain is greater on SSDs with lower row random write IOPS because of the high write reduction ratio. As a result, MBPPL can achieve higher performance with low-end SSD than vanilla with a high-end SSD. To evaluate recovery time, we simulate the file failure by crashing the system for 10 minutes while running the TPC's benchmark. This is the recovery result. During the analysis phase, MBPPL spends 3 more seconds for scanning the evidence space. However, in the redo phase, MBPPL significantly reduces read time by skipping redo for PPL pages. To assess the impact of PPL-based version construction on HTAP, we extend the TPC's benchmark with an additional thread executing long-lived transaction query. PPL-MV is MVPPL with PPL-based merge versioning, and MVPPL without it is just the baseline version. Thanks to constant time version construction, PPL-MV significantly reduces version build time. It only takes 1/10 of the average version construction time compared to MVPPL. We also test the PPL-MV with varying warehouse size. The relative benefit of PPL-based version construction decreases since the data rate grows, version chains become shorter. Moreover, PPL-MV results in a milder drop in transaction throughput. This is because PPL-MV reduces undo page risk, so OLTP pages can stay in the buffer longer, which improves the hit ratio. In conclusion, I introduced MVPPL, which leverages MVDIM as a durable per-page little log cache. By storing per-page little logs in MVDIM, we can dramatically reduce writes to SSDs. This also enables a leaderless, unduless recovery and redo-based merge versioning. I want to say it's time to revisit MVDIM. Thank you for listening, and please check out our paper and code. In the paper, we discuss more details of MVPPL and especially how to support multi-versioning by leveraging PPLs in MVDIM. As part of our future work on MVPPL, we are currently conducting experiments using CMMH. If you have any questions, please feel free to reach out. Thank you for listening.